Yeah, so good afternoon, everybody, and welcome to the 7th QOQI Colloquium. So today is really a pleasure to have our guest, Jack Harris, giving the talk. So let me briefly introduce his profile. So he studied physics at Cornell University. Then he did a PhD in the University of California in Santa Barbara. He got the PhD in the year 2000 under the supervision of David Auschulow. And his thesis was on studies of high sensitivity magnetization of semiconductor heterostructures. Then Jack went as a postdoc to the Center for Ultracold Atoms in MIT and Harvard. He stayed there 3 years working with John Doyle and Wolfgang Ketteler, who are very well known here in Innsbruck, of course. And then in 2004, he became assistant professor at Yale. And he progressed, becoming tenure in 2010 and full professor in 2017. So the research interests of his group have to do with the quantum aspects of motion, both at the microscopic scale and the macroscopic scale, at both scales. Actually, in the microscopic scale, he was interested in the quantum motion of electrons in semiconductors, and he and his team did a very important experiment where they observed persistent currents in metallic rings, which were in a normal state, not superconducting. But due to quantum effects, they saw persistent currents, which was very, very nice and very surprising. Then on the macroscopic scale, he's one of the pioneers of the field of cavity optomechanics. He has done seminal experiments in the field. In particular, 2008, they observed strong dispersive optomechanical coupling between light and a micromechanical membrane, and this is now known as the membrane in the middle experiment. So they cool down and show a strong coupling of the motion of the membrane. Also, he has done recently very nice experiments on topological energy transfer in optomechanical systems using exceptional points. That's a topic he's also very interested from the theory side. And actually, I want to also advertise that tomorrow Jack is giving also a theory talk at 2 at the seminar round 1 on precisely that, on exceptional points and dynamics of non-Hermitian Hamiltonians. So we're also invited for that talk. And recently, he has also been very interested in doing optomechanics with superfluid helium, which will be the topic of this talk. So Jack has got many awards and fellowships. So in particular, as a young faculty, he got several fellowships. Also, he got the DARPA Young Research Award in 2009, the Arthur Greer Memorial Prize in 2009. He became APS Fellow for the AMO division in 2016, and very recently, this year, he got a very nice fellowship from the Department of Defense, the so-called Vannevar Bush faculty, which provides very generous funding, even more than the ERC advanced grant here in Europe for a single group in the US. So that's very nice. So it is for all these reasons that we are very happy to have you here, Jack. So thank you very much for coming, and we look forward to your talk. So please, let's welcome our speaker.
Thank you. So thank you to Oriel for the invitation to be here. And for patience with my incompetent travel skills over the last day. Missed airplanes, forgot things at hotels, but it's been okay. It's a real pleasure to give this special colloquium here at QOQI and to visit the University of Innsbruck, where there's so much exciting and groundbreaking work going on in quantum optics. It's also a real pleasure to be here for 3 days, so I look forward to having relaxed conversations. There's a lot of room in my schedule if you want to chat about stuff later on. I'll be around and more than happy to talk. So the main point of my talk today is to introduce you a bit to what you might regard as a subfield of quantum optics, which is the field of optomechanics. And the particular motivation that I'm going to give for this field is thinking of it as a way to explore quantum phenomena in macroscopic systems. So I'll start with a bit of an introduction about why we want to do that, why optomechanics is a promising way of doing that. And then for my own group's research, I'll tell you about why we've come to look on liquid helium as a great material to build quantum optics devices in general out of, and quantum optomechanics in particular. And I'll describe 2 experiments which are kind of shown quickly as photographs here, one consisting of an optical cavity conventional, more or less, just filled with liquid helium. And the other experiment, which is less far on in terms of scientific results, but about which we're very interested, is a device consisting of a millimeter-sized drop of liquid helium magnetically levitated in vacuum. So those are the two projects I'll try to tell you about. But first, let me give you a sort of introduction to how I think about this question of macroscopic quantum phenomena. So the first thing you have to say about quantum mechanics as a theory is its success is hard to overstate. It's provided us with a description of the basic constituents of the matter we see around us, a description of how these elements bond to each other, how they interact with each other to make either phases of matter or useful devices. It's provided us with the laws we need in order to design medicines and materials, and the imaging techniques to tell us things about the workings of the body that would never be accessible without this knowledge. That kind of knowledge has grown into inorganic technology as well, things that have revolutionized society, and have provided us with increasingly sophisticated instruments, lasers, GPS, even LIGO, which then allow these sophisticated, powerful instruments to be turned back on the basic questions underlying the theory of quantum mechanics in the first place, and to provide us with increasingly precise tests of the theory of quantum mechanics, which, of course, it should be said, passes with flying colors every time. So this is the great story, and at the same time, there's a certain level of discomfort with this theory, which is listed here. Quantum mechanics as a theory tells us that there are phenomena in the world that are very counterintuitive to us, and you've certainly seen lists of these phenomena here. Rather than these specific phenomena, maybe what I would mention is that the laws of quantum mechanics have a character which is, I would say, inconsistent with the character of the laws of the world that is accessible to our senses, the laws of classical mechanics. And in particular, it's maybe hard to summarize these very briefly, but some of the deep features of quantum mechanics that are in contradiction to our usual sense of the classical world is the fundamental rather than emergent appearance of indeterminacy, the apparently fundamental role of non-locality, and even the fundamental role of information. And these are hard things to draw cartoons of, but the way that I would try to draw them as cartoons is that in quantum mechanics it's not possible to describe, certainly at least a many-body system, in terms of distinct objects moving independently in three-dimensional space. Likewise, the second cartoon is intended to illustrate the fact that quantum mechanics tells us that the evolution of a physical system, let's say of a subsystem, depends on how information about that subsystem, the yellow robot, is stored in other subsystems. That's a feature that just doesn't exist in classical mechanics, except in sort of emergent senses. So quantum mechanics is really very, very different than classical mechanics, both at a phenomenological level and at sort of a philosophical or broad-scale view of the theory. And you can regard this knowledge as providing you with some deep insight into how the universe is really built. You can regard it as providing you with some new resources for building computers or doing cryptography. You can regard it as providing you with some fundamental limitations about how well you can ever hope to measure passing gravitational waves or very small signals. But one big question that it invariably raises is, at the end of the day, we're all going to walk out of here and go get a cup of coffee at the coffee machine, and we're not going to worry about this. All of us are going to behave like distinct solid objects in three-dimensional space, and we'll find our way to the coffee machine. So somehow a classical world that is very accurately described by classical mechanics emerges from these laws. And in the last couple decades, I think the program of decoherence and understanding about environmentally induced selection and the like has provided us with at least a fairly clear story of how this classical world emerges. There's certainly a lot of interesting work still to be done in understanding that. But the particular question that I want to ask is whether it's plausible to think that the classical world at the level accessible to our senses might still retain measurable aspects of the fundamentally quantum nature of its constituents. That's what I mean by macroscopic quantum phenomena. And the answer to that question, I think I could give a motivation very simply without any sort of deep theory, just by asking the following question. Suppose that I have a harmonic oscillator, a system that we understand perfectly well, And I want to ask, why is it that in my everyday life I don't have to worry about any of its quantum mechanical behavior? So for a macroscopic scale, let me take something with mass of 1 and frequency of 1 in the natural units of our everyday lives, which is to say MKS units, and then ask, well, quantum mechanics, where would I expect to see signs of your laws? And one place that I could look would be that quantum mechanics would tell you that, hey, this object can never be at rest. If I remove all of the energy from it that I can and measure its position, I'm going to see that it looks like it's fluctuating constantly back and forth, even though I've removed all of its energy. And of course, if I plug in numbers and ask, well, what is the size of this 0-point motion? That's for these parameters, that's going to be 10 to the minus 17 meters of motion. And usually quantum mechanics textbooks will say, well, this is why the world is classical, because that's an absurdly small number once you plug in reasonable masses and frequencies. On the other hand, if we look more closely at that, the story is more complicated. The thing that this is very small compared with is sort of the basic unit of length of our senses, which is the wavelength of visible light. 11 orders of magnitude too small to resolve with a standard optical instrument, whose resolution is going to be set by the wavelength of light times some factor of order unity, depending on how good your optics are. Of course, in the last couple of decades, simple, in finger quotes, classical macroscopic optics have given us very powerful tools for manipulating light, and specifically what I'm referring to are high finesse mirrors. So macroscopic pieces of glass that you can hold in your hand can be coated with very high quality materials that, if you like, allow a photon to pass into this space, but then force it to bounce back and forth maybe 1,000,000 times before finally releasing it again. And as a result of that, any displacement of this mirror imprints a phase on the reflected light that's amplified by this number of bounces, a parameter known as the finesse of the cavity. So immediately, that provides your classical optical instrumentation with a factor of 1,000,000 in sensitivity over just the bare wavelength scale. Furthermore, one can take the transmitted light and note that, yes, it's going to go from 100% reflection to 0% reflection on a length scale that's sort of 1,000,000th of a wavelength of light, and not just look for the reflected light to go from a watt of laser light to 0. You don't need to do that. You can just sit on the steep part of this fringe here and look for some very small change that is, part of this overall change from full reflection to 0. And so with good electronics, basically look for small fluctuations in this intensity. And good electronics these days means detecting a change of about 1 part in 100 million. So with this modern electronics and modern optics, we're allowed to take the factor of order unity that appears in our notion of optical resolution and turn that into 14 orders of magnitude, which means that with tabletop optics, in fact demonstrated, for example, in the Paris group, it is possible to look at a centimeter-sized lump of glass and measure its displacement with a resolution of 10 to the minus 20 meters in 1 second of averaging time. That's, at that point, yes, your reaction should be one of audible surprise and amazement. Not least because, remember this number here. So suddenly that means you have 3 orders of magnitude of sensitivity to detect the 0-point motion of a 1 kilogram object. And yet, no one has. So why is that? Well, the reason is that it's very hard to really remove all the energy of a 1 kilogram, 1 hertz object. If that object is, say, coupled to room temperature, it will have thermal motion that's 1,000,000 times bigger than the 0-point motion. And most frustratingly, this thermal motion has all of the same qualitative features as the quantum motion. So you can build this incredible displacement sensor and watch this object, and 999,999 parts of your fluctuations will be this. In principle, 1 part in 1,000,000 will be from this, but you have no way of saying which is which. So in practice, that hasn't worked out yet, but nevertheless, these are the basic ingredients. So what you can take away from this is that the quantum effects in a macroscopic objects are accessible in principle. What you need is some sort of high finesse optical readout. You want that readout to be nicely coupled to an object that is as cold as possible and whose interactions with the bath are as weak as possible so that you can get rid of this kind of motion here. Those are the main ingredients. If you can do that, though, why would you want to? So far, all I've said is you might be able to reproduce textbook quantum mechanics in surprisingly large objects. Well, I think there are three reasons for doing this. One is just pure intellectual curiosity. For my money, the fact that Marcus Arndt's group in Vienna can take a molecule that looks like this with nearly 1,000 atoms and launch it through a vacuum chamber and have it pass through real physical slits, real holes in something, and then look where those atoms end up on a screen, and this is real data, and see the matter wave interferometry that is due to the wave function of this object's center of mass motion. To me, this is amazing and changes the way that I think about what physics is and how our universe works. And if this is all that the field ever did, was to do this with increasingly big objects, I would think that would be a noble scientific goal. At the same time, mechanical sensors and micromechanical sensors are part of a very robust and sophisticated technology that's used in all kinds of situations for all kinds of applications. And if you can take a powerful and sophisticated technology and add to it quantum functionality, there's probably win to be had there. Lastly, and most speculatively, it is possible that the quantum mechanics of sufficiently massive objects is not just the trivial quantum mechanics of less massive objects. It is speculated that, if the Schrödinger equation is really only an approximation of some higher order dynamical equations of motion with nonlinear terms, that these nonlinear terms might be accessed with macroscopic objects. It's speculated that a sufficiently massive object, and by massive I mean massive enough to change the geometry of space-time around it, to source its own gravitational field, that its behavior when it's placed in superposition might tell us something about how the quantum physics of the gravitational field works. I don't know, exactly how seriously to take these speculations, but there's certainly a field in literature out there that considers this as a possibility. So I think all three of these are reasonable motivations. Again, all three of them, whatever your motivation is, it's really these technical requirements that one has to meet. Very sensitive optical instrumentations, measuring the positions of very cold, high-quality objects. So that brings us now to the topic of optomechanics as a particular way of realizing this. And the basic starting point, intellectual starting point for optomechanics is really the one that was raised by Einstein and Bohr in their debates, and then soon after by Erwin Schrödinger in a letter to Albert Einstein, where the basic idea is the one of Schrödinger's cat, that unitary evolution in quantum mechanics means that if you have some microscopic degree of freedom that you believe you can prepare in a superposition, something like a photon or an electron, something we really believe quantum mechanics applies to, and you can couple it unitarily to anything, then no matter how big that thing is, just unitary evolution, according to the appropriately chosen interaction Hamiltonian, will result in that other thing, indicated by the capital M here, becoming entangled and itself in a quantum superposition. So in optomechanics, the thing that we really believe is a microscopic degree of freedom that we can prepare an interesting quantum state is the electromagnetic field. The unitary evolution between electromagnetic field and some macroscopic degree of freedom doesn't come about for free. When your eyeball absorbs a photon of light, we usually don't think of that as exactly unitary. But radiation pressure does provide a unitary coupling between the displacement of a mirror and the photons that happen to be bouncing off the mirror. So the unitary of radiation pressure coupling provides us with this key ingredient. And the basic recipe of optomechanics then being that if you can prepare photons in some reasonably well-controlled quantum state, inside a cavity they can interact unitarily with some massive degree of freedom and place that massive degree of freedom in some kind of interesting quantum state. Unlike the thought experiments of Einstein and Schrödinger, we don't have direct access to this thing, though. We can't easily go and look at it and see, yes, it was in a superposition. What we really have access to is the light that comes trickling out of this experiment. And so somehow it's going to be measurement of the light that leaves the system we're going to have to use to infer whether or not there was any interesting quantum mechanics in this massive object here. So this is optomechanics in a nutshell, and one of the main figures of merit for it is this coupling rate G0, which loosely speaking tells you how often a photon inside this cavity exchanges its quantum state with this massive object. And in most, maybe all optomechanics experiments, this is the smallest rate in the problem, which is not the situation one has in cavity QED of atoms or superconducting circuits. Nevertheless, it's a fact of life that we somehow work with and try to still extract some interesting physics from. But it's really the smallness of this parameter that's an outstanding challenge in the field. Okay, and so that brings me to the question of how are we going to actually construct such an object? And let me just say that if you were starting from scratch and didn't know how people really build mechanical oscillators and optical cavities, and you just had to go to the catalog and pick a material that you were going to use for your construction, superfluid liquid helium is probably the thing you would order out of the catalog. Why is that? Well, if you want low mechanical friction, here's a material with identically zero viscosity. If you want to blast high-power laser light at it to try and measure it really strongly, here's the material with probably the lowest optical absorption of anything you could find in the universe. If you want to actually have it stay cold while you're blasting it with light, it's nice that it has the highest thermal conductivity at very low temperatures of any material. And if you want to look ahead and think about exotic quantum hybrids, liquid helium can play host to a lot of interesting atom-like defects. Okay. So you order your can of liquid helium, you bring it to the machine shop, and you say, please put this in the milling machine and carve me an optical cavity out of this. This is really going to be the best experiment I can think of. Okay. And the machinists look at you like you're crazy, and so that's not what you can do. So you have to do something else. And in our first experiments, what we did was to build an optical cavity, not literally out of the liquid helium, but using more or less conventional Fabry-Perot optical cavities that are unconventional in the sense that they're formed on the end faces of single-mode optical fibers by our collaborator Jakob Reichel in Paris. And these provide us with a really nice, stable, pretty small optical cavity whose mode is nicely coupled into the fiber's traveling wave modes. And if you're working inside of a cryostat, this is a really nice, robust, reliable way of building an optical cavity and actually getting light into it. So the actual device looks like this. These are two glass ferrules here. There's one, there's the other. Each has a hole drilled in it, and each one has a fiber inserted into it. And those, from the opposite sides, those two fibers meet and are facing each other right here in this zoom in, and it's between these two ends of the fibers that we imagine the optical field being confined. And on its own, this is not a very interesting system. This is an empty cavity, but what we do is simply place it in a bucket of liquid helium attached to a dilution refrigerator. We fill it with liquid helium, and at first, this was very frightening to me, because the only thing that I knew about liquid helium is that it is famously complicated. You have the two-fluid model, you have vortices, you have mutual friction, you have first sound, second sound, third sound, fourth sound, and zeroth sound. And if you have zeroth of anything, it either means that it was being discovered by computer scientists or set theorists who start counting from zero, or that somebody found a whole bunch of them and then realized there was one that should have been back at the origin. And I didn't want to learn about any of this stuff, and it turns out you don't have to. So as long as the liquid helium is sufficiently cold and there's no violent motion in it, then you can take the multi-component Navier-Stokes equations and linearize it appropriately, and you find that it reduced just to the scalar wave equation, which is the same thing as saying that sound exists in liquid helium, and we're going to use that sound, those density waves. Not only does sound wave exist, sound waves obey more or less the same wave equation and satisfy the same boundary conditions as the optical modes. They see those glass surfaces as mirrors as well, and so they're going to have exactly the same family of transverse modes and longitudinal modes, the density waves now in the helium, which I'm showing as blue here, and those are going to overlap necessarily perfectly with the optical mode because they're defined by the same surfaces. And that's a nice thing to have in any sort of cavity QED type of experiment. So the actual way that this standing wave of light couples with this standing wave of sound is just because a sound wave is a modulation of density, and the density determines the material's index of refraction. That's all that's going on here. And I can draw you a cartoon of that by showing the optical intensity of some low-order optical standing wave. And then if I consider the following sound wave with exactly half the wavelength and animate its oscillations, this is what the liquid helium is doing as a function of time. And you can see that at some instance of time, the light is overlapping with a lot of extra helium, and half a period later, all the light at this antinode is overlapping with too little helium. And so even though there's no mirror moving, As far as the light is concerned, this is a cavity whose optical length is changing, is oscillating at the sound frequency. And so this is the same thing as physical length oscillating. And so this is, even though it's constructed in this odd fashion, this is a totally canonical optomechanical system that is physically the same thing as the cartoon I showed you of a Fabry-Perot cavity with a movable end mirror. It's the exact same thing. Okay, it turns out that in order for the light wave to overlap with sound waves in this way, one has to have light whose wavelength is twice the acoustic wavelength, which means that if your light is at 200 terahertz, which is what we use, the sound wave is going to be at 315 megahertz. The speed of sound is very different than the speed of light, so same wavelength gives you very different frequencies. But that's the basic construction of the experiment. So now we could ask, well, okay, we have sound, we have light, they're going to talk to each other. Where should we look for specifically quantum mechanical effects? And this is the basic story, simplest story you can tell in quantum optomechanics. I'll provide a quick introduction to it. If I have an optical cavity and I send in green laser light, I expect green laser light to reflect from those mirrors. But if one of the end mirrors can oscillate at a certain frequency, then let's not rush to quantize anything. Let's just, these are all big objects. Then as this mirror moves back and forth, it's going to imprint phase modulation sidebands on this light. You could even think of that as Doppler shifting the light. And so the light that comes out to lowest order is going to have a red sideband and a blue sideband. And the power in those sidebands is going to be proportional to the power of the motion, if you like, the energy stored in the motion, the mean squared displacement of the oscillator. And if you were in a rush to jump into quantum mechanics, you could say, well, that's proportional to the number of phonons, the number of quanta in that oscillator. But no one would believe that you had measured the phonon number. You've just measured the mechanical energy, which has a perfectly legitimate classical description. The way that quantum mechanics emerges first in this story is to say, well, let me say that I really do believe that light is made of photons, and when I put a detector here, it really is sometimes going to give me a click when it actually absorbs one of those photons. Now, if I'm only sending in green photons, and I know that sometimes I get blue or green or red photons out, then somehow each click at the detector represents an instance in which one of these green photons has either been left alone or promoted to blue light or demoted to red light, decreased in energy. And that energy has to have come from the mechanical oscillator, and if I calculate the matrix elements for these processes, and then the rate at which they occur, the rate of producing blue light is just like in the classical case, proportional to the mechanical energy stored in the oscillator. But because of the way raising and lowering operators work for harmonic oscillators, the rate at which I produce red sideband photons is proportional to the number of quanta in the mechanical oscillator plus 1. So no matter how you think about this, this is a feature that you might measure that involves a single quantum of energy. It involves somehow the quantum mechanics of this macroscopic object. Okay, so from a practical point of view, you could do this at room temperature, and your mechanical oscillator might have 1 billion phonons, quanta in it, and you might look at this light very carefully and say, oh, I've measured 1,000,000,001 sideband here, but only 1 billion here, and in principle, you could do that, but it would be difficult to convince anyone that you had done that correctly. So in practice, it might be nice to have this mechanical oscillator cold enough that the mean phonon number was really of order 1 or 0 or a few, such that this difference in the sideband would be readily appreciable. And for the 300 megahertz acoustic modes we're thinking about, this means temperatures of about 20 millikelvin accessible in a dilution refrigerator. So that's exactly the experiment that we did. We took the device that I showed you, placed it in a dilution refrigerator. For various technical reasons, we were measuring the red and blue sidebands by sending in 2 different laser lights, one far detuned to the blue side, one far detuned to the red side, such that their motional sidebands were nicely within the bandwidth of our measurement. And then we also reflect from the cavity a local oscillator laser beam so that in the photocurrent spectrum, we have nice independent records of these 2 motional sidebands. And this is the data shown here. This is the raw Fourier transform of the photocurrent of the beat note between the local oscillator and these mechanical sidebands. And of course, there's a noise floor. There's a photon shot noise contribution to that. But these are the mechanical oscillations. These are the Stokes and anti-Stokes processes of phonons in the liquid helium being added and subtracted by the light. And we go through a lengthy process of careful calibration in order to convert this signal to a normalization first subtracts off the noise floor and then normalizes it such that the height of these features is the height you would expect from a thermally populated acoustic wave whose mean number of phonons is given by the height of this peak. And once we do that, you can see that the difference between the blue and red sideband is of order 1 phonon in these units. Of course, that difference is riding on top of a largish background. Here we're at a temperature where you'd expect sort of 7 or 8 or 9 phonons in the acoustic mode. And so anyway, this is the n, and this is maybe the n plus 1. In the experiment, we also have access to the real-time signals from both of these sidebands. We can cross-correlate those and look at the spectrum of cross-correlations. For the experts in the audience, this doesn't provide any substantially different physics, but it does provide a sort of nice extra set of technical cross-checks to make sure we're not fooling ourselves. And again, standard quantum optomechanics predicts that these cross-correlations arise exclusively from the quantum fluctuations, and in these units would have magnitudes of 1/2 phonon. So here is all that data now more or less collapsed on top of each other. The blue sideband, whose height is just proportional to the thermal fluctuations. The red sideband, whose has contributions from the thermal fluctuations, but has an extra contribution from the quantum fluctuations, and then the real and imaginary parts of the cross correlations of these data. And I will say for sure, it is possible to shine light on something, collect that light, see how much red and blue there was, and have unintentional filtering in your experiment that would give you apparent asymmetries like this. So there are a lot of cross-checks that we go through to make sure we're not fooling ourselves. One of them is to just look at how this data varies as we change the temperature of the device. So as I make the device hotter or colder, I would expect this blue peak just to get bigger or smaller in proportion to the device's temperature. And so here's the height of that blue peak as a function of the device's temperature. It looks like we understand sort of how our device gets hotter and colder. Let me now consider all of the quantum signatures, so the difference between blue and red and the height of these two cross-correlation signals, all converted such that if they were originating from quantum fluctuations, they would have magnitude 1. And so these are those 3 different signals, sideband asymmetry and real and imaginary parts of the cross-correlation as a function of the device temperature. And what you can see is they don't seem to have their origin in anything that depends on temperature, and they have the size predicted by quantum optomechanics. In principle, we could do this experiment all the way up to room temperature, but in practice, it would become impossible to distinguish this difference. So this is the basic conclusion of this part of my talk, that you can take a Fabry-Perot cavity, fill it with liquid helium. We don't cool it quite to the ground state, but even with a finite thermal occupation, we can distinguish these distinctly quantum mechanical features that have to do with the quantum mechanics of the sound waves in the liquid helium. And I want to thank our collaborator Jakob and the 3 graduate students who really carried out this experiment. I should also say I'm happy to take questions in the course of this talk, and this would be a particularly natural place since this is sort of the end of this part of the discussion. Yeah.
Here you've used the cryostat for setting the temperature.
Yes.
Have you tried something else?
Like laser cooling?
Like laser cooling?
It doesn't work very well in this device for a variety of technical reasons that are not super interesting. But I can tell you about later. Oh, sorry.
Well, I've just one sort of a minor question. So there have been these beautiful experiments where one takes, for example, cold atoms, Stanford Kern, Berkeley, and so on, and puts them inside of cavity, which is also a form of a gas and not a liquid. So can you sort of discuss a little bit what the relation is of these kind of experiments with the one that you do here? Because normally I have to say when I think about a harmonic oscillator, I really think about a solid and not a liquid or a gas. Mm-hmm. And so there's actually some differences, and maybe I can comment on that.
There are some differences. I don't think any of them are apparent here. So because you can take the Navier-Stokes equation and linearize it for small excitations, and we're dealing with small excitations here, they are just the normal modes of the elasticity equations, the exact same as the normal modes of a solid object are the normal modes of the linearized elasticity equations. In Dan Stamper-Kern's experiment, they're looking at the center of mass motion of a gas, which is maybe also a condensate in some of the experiments. Here we're looking at phonon modes rather than center of mass modes. There's a lot that's similar. I mean, I would say at the quantum optics Hamiltonian level, these are all the same, and there are differences in the realization. I mean, this is probably a nanogram of material, as opposed to something more like a yoctogram in Dan Stamper-Kern's case. That's a distinction that means a lot to us as experimentalists, but that wouldn't appear immediately sort of at the Hamiltonian level.
It's more like a technical. So the refractive index of liquid helium is very small. Is the imaginary part also small? Is this all known, or?
It is so small it is unknown. So liquid helium has a band gap of 19 electron volts. It's the biggest band gap of any condensed matter material. Much more importantly, it has 0 defects. So it has no chemical impurities, it has no structural impurities, has no mid-gap states whatsoever. If you put the wrong kind of atom into liquid helium at 20 millikelvin, that atom just hits the wall and freezes solid forever. So the imaginary part is probably as close to 0 as you could ever imagine.
And the real part is not too small to measure.
It's 1.028, which is a disadvantage, but combined with everything else, we still like it. Yeah, we wish it was 2.5 or something. But it's not. Okay, so that's the end of this part of the talk. These are the conclusions that I would like to advertise and that I would like you to remember. These are the conclusions that I would like you to ignore and pretend aren't here. So the first of these is that, yeah, these are effects that we would ascribe to quantum mechanics, but they are the least dramatic of quantum mechanical effects. These are just fluctuations whose size happens to be set by h-bar. This is not something deeply quantum mechanical like a violation of a Bell inequality or something like that. We would like to look at these stronger quantum effects with macroscopic degrees of freedom, but in order to do that, we have to get out of this sort of prison of harmonic oscillators that are linearly coupled to each other and weakly measured. And so we don't have a lot of ways of making either these optical cavities or acoustic cavities nonlinear. Instead, what we would like to do is to borrow a page from other workers in this field and make use of the inherent nonlinearity in strong projective measurements. And there the basic idea comes back to this drawing that I was showing you before. And in principle, each time this detector goes click, it knows at some level whether it saw a green photon or a blue photon. And every time it sees a red photon, let's say, that means that it has lowered the, it has raised the quantum number of this mechanical oscillator by exactly 1. And if you like, the back action of that measurement would take this mechanical oscillator from, say, its ground state, if that's where it was, to a state with exactly 1 quantum of energy in it. And that's a quantum state where you can start to see more exotic quantum effects, things that aren't just basically fluctuations. The problem, and this was pointed out by a number of groups, and experiments making use of this have already been carried out in the Vienna and Delft collaboration. The difficult thing here is that these frequency separations are very small, 300 megahertz, and the overwhelming majority of photons go in and come out without being shifted. Only about 1 in 10 to the 8 is one of these interesting blue or red sideband photons that's somehow changing the state of the quantum oscillator. So what we need is a way of having a detector that really only goes click for one of these interesting blue photons and not for any of the other guys. And really the best idea I've heard so far is just brute force filtering. So one puts a sufficiently narrow filter here that only passes, say, the red sideband photons, and then when this detector goes click, you can plausibly believe that it has detected a specifically red photon and that is going to project the mechanical oscillator into some interesting quantum state. So this is hard, bit of filtering, but in principle, it's straightforward. So what I'll tell you about now is the exact same experiment, the exact same device, where we've just added to it a whole bunch of cascaded filter cavities and a proper single photon detector. And the way this is all very preliminary, this is not really publishable yet, but just to show you where we are, the way the experiment works is we just turn on one laser beam, say detuned by a mechanical frequency, And if an inelastic process happens with the mechanical oscillator, we'd expect one photon to show up here that's more or less resonant with the actual cavity and that passes resonantly through these filter cavities, and we'd expect it to end up at the photodetector. And this shows the photon count rate as we take this drive frequency and scan it back and forth. And when it's not at the right frequency, we just have some background. But when it's at a frequency such that the inelastic scattering is producing photons that can actually pass through these filter cavities, we get extra counts. And in principle, though there's nothing here to prove that to you, each one of these counting events is projecting the mechanical state into some interesting quantum state. Likewise, we can do the same thing on the red side. Again, the difference between these two peaks would be something like what I just showed you before. I think in the interest of time, I won't spend a lot of time telling you about the details of this data, which we're still analyzing. But loosely speaking, we're starting to take this data, look at the heights of these blue and red sideband features, the counts, if you will, and just make sure that they are telling a story about sideband asymmetry that's consistent with what we've already seen. And very loosely speaking, the answer is yes. As you crank up the laser power, both sidebands go up. This is because the device is just getting hotter. The sideband signals are also splitting. This is also what you expect because of laser cooling or laser heating. The blue data is taken with a laser beam on the blue side. The red data is taken with a laser beam on the red side. But if you extrapolate these trends back to zero laser power, there is a little difference here, which is at least numerically consistent with the expected quantum sideband asymmetry. So this is all pretty rough at this point, but this is where we're headed with these experiments. What we'd really like to do is to make tests of things like Wigner function negativity by looking at the actual statistics of red counts and blue counts in something like real time. And I should say that things like this are being done by the Delft and Vienna group with their optomechanical crystals, and so we very much look forward to stealing all of their good ideas and implementing them here, not just because we want to copy what they're doing, but because these devices, though they're described by the same Hamiltonian, are vastly more macroscopic. We're talking about mechanical oscillators that are 1,000 times more massive, and so it'd be interesting to look at these non-Gaussian quantum effects in their oscillations as well. So again, here I have to thank the grad students and postdoc Yogesh who have really led these projects. And these are the conclusions that I want you to take away. And again, there are some conclusions that I would like you to ignore and that I would like to just sweep under the rug, which is that at the start of this talk, I said that liquid helium is this amazing material. You should go to the machine shop and endure the humiliation of their laughter when you say you want to build a device out of this stuff, because it's going to have all these amazing properties. And at the end of the day, the devices that I told you about are good optomechanical devices. They're state-of-the-art. They're competitive with anything else you build, but they're not like magically wonderful. There was no manifestation of the strictly zero viscosity or the total absence of optical absorption in this material. In fact, our devices got hot when we shone laser light on them. And all of that comes about because the device is built out of liquid helium, but also out of conventional optical materials. And those absorb light. They get hot. They dissipate acoustic energy. And so the real takeaway from these experiments is that superfluid liquid helium is amazing, but those amazing properties are compromised when you put it in a can made of glass. So the project that we've been developing is to get rid of the can altogether and instead build an optomechanical device that is truly constructed only of superfluid helium and vacuum. And so here the idea is to take a drop of liquid helium, maybe a millimeter in size, and levitate it magnetically in vacuum. The idea being that this dielectric sphere can serve as an optical cavity by trapping light in whispering gallery modes, and then it can also serve as the mechanical element because the drop can oscillate, if you like. It can slosh back and forth in its shape. It could even rotate. And this is a pretty unconventional kind of device, but the reasons that we were optimistic about actually building it, and of course, a sloshing drop with lights confined in a whispering gallery mode is definitely identical to this canonical optomechanical system. Such a device has never been built before, but all of its main ingredients have been demonstrated. So you can use powerful superconducting magnets to levitate centimeter-sized drops of liquid helium. This is demonstrated at Brown University. It's known that liquids, mostly at room temperature, like ethanol and water, do make such smooth, perfect shapes that they make really good whispering gallery mode cavities. And it's known that when you take liquid helium and spray drops of it into a vacuum chamber, it's known that the liquid helium evaporates very efficiently and cools itself very effectively. In these experiments, the drops were not in any way confined, so they only lived for a millisecond before they hit the wall of the vacuum chamber. But nevertheless, all the evaporation physics was very well understood from these drops. So we just want to combine all three of these things together. Just as a couple of quick summaries about the kind of performance we hope from such a device, if you trap light inside of a dielectric sphere in a whispering gallery mode, there are various ways in which that light can be lost. In a proper solution of Maxwell's equations, you find that there is a bit of leakage out of the drop. That leakage is exponentially small in the sphere's radius, so we expect that hopefully not to be important once the drop is of order a millimeter or so. One can also, in any sort of conventional optical material like glass, one has just absorption in the glass. Glass is not a perfect dielectric. One has scattering of the light from impurities. We expect both of these to be truly absent in liquid helium. Liquid helium does have thermally excited density fluctuations. You can estimate a finesse on the order of 100 billion from those. Probably the main limitation will be the fact that a liquid drop can have thermally excited surface waves, which look like a kind of roughness and can scatter light out of these modes. This turns out to be a little bit tricky to calculate properly, but we hope that we can still get kind of world record or better optical finesse just by building a cavity out of liquid helium. At the same time, we want to do not just have a really good cavity, we want some mechanics, so we want some degrees of freedom. A levitated drop, of course, can just move back and forth in the trap. That's not what we're interested in part because magnetic traps are quite weak and that motion would be at 1 hertz, but also because that motion doesn't actually detune the optical cavity. It just carries the optical cavity back and forth. One kind of motion that would be much more interesting is the surface deformation of the drop, oscillating from prolate to oblate, and so stretching a whispering gallery mode that lives at the equator. That's motion that's at a little bit higher frequency, and because liquid helium is such a soft material from the point of view of surface tension, the 0-point motion of these oscillations is absurdly large, such that the single quantum coupling, the phonon-photon coupling rate, it doesn't look numerically large, but is larger than some of the other scales in the problem. And this is unusual in optomechanics. So this here is a plot as a function of the drop radius of the frequency of oscillation of a low-order surface mode in blue, the expected cavity line width in purple, and the single quantum coupling rate in green. And you can see that under these assumptions, it should be possible to reach a situation in which actually the single quantum coupling rate is even the largest scale in the problem. That would certainly be a very exciting bit of progress. One other thing that we're interested in is that a levitated drop of liquid helium has a degree of freedom, a low energy degree of freedom that is not a harmonic oscillator. And as I mentioned, there's a sort of prison of Gaussian quantum physics associated with systems that consist only of harmonic oscillators. So if you have a freely suspended object that's truly isotropic, as liquid helium is, suspended in a trap that has at least cylindrical symmetry, which any superconducting magnet provides to a very high degree of accuracy, that object is free to rotate, and just rotate endlessly without any sort of confinement of the angular direction. And free rotational motion, of course, is not a harmonic oscillator. It has a different quantum mechanics, which I'll say about in a minute, and it's motion, nevertheless, that still couples strongly to the whispering gallery modes just via the centrifugal bulge. So you know that the Earth rotates, and as a result is a bit oblate. The same phenomena will stretch a whispering gallery mode by an amount that's proportional to the square of the component of angular momentum normal to that whispering gallery mode. And that's of interest because in quantum optomechanics, usually we're measuring harmonic oscillators where the degrees of freedom x and p have an algebra that means that those variables, in particular position, are not really well suited to QND measurements. You measure position at one time, the back action will alter the result of a measurement of position at a later time. Angular momentum, of course, as is well known, is described by operators that satisfy a different algebra. So when you measure the z component of angular momentum, as this whispering gallery mode would, the back action is on the x and y components, which at later times do not necessarily manifest in fluctuations of L sub z. So this is a situation in which the optical cavity can be used to perform a quantum non-demolition measurement of a degree of freedom of this massive object. Okay, so those are some of the things that we're thinking about. In terms of the actual experiment, you just buy a very powerful superconducting magnet with some extra bells and whistles. At the end of the day, a 15 Tesla magnet with a large magnetic field is enough to levitate liquid helium, even though liquid helium is not exactly the world's most magnetic object. And the experiment consists of this superconducting magnet with a vacuum can inserted inside of it. The only thing you really need to know about it is that it has a window. We'll be looking up through the window here. And then there are two 45-degree mirrors. So we're going to see everything that happens at the levitation point in triplicate, just like when you go to buy some clothes and look at yourself in those extra mirrors there. The experiment works by filling the chamber with liquid helium, enough that we get a puddle at the bottom. And then here's the view of that. These are the 45-degree mirrors here. This is just looking straight up through the bottom. Then in the experiment, we suddenly open this chamber to a pump. That pump causes a non-equilibrium fog to form above the liquid helium. The pump is trying to pull all those fog droplets out of the magnet. The magnet is trying to hold on to all those droplets. The droplets are bumping into each other and trying to reduce their surface energy by coalescing into a large drop, and it's a giant fight between all of these processes. But what I'll show you now is a video in which at the start we're looking up through a puddle of liquid helium, and we'll open the valve to the pump. Everything will go black for a second as the fog forms, and then immediately in the aftermath, you see all these droplets swirling around, bumping into each other, and gradually forming this millimeter-sized drop of liquid helium that is fully suspended, at this point not in vacuum, but in a modest amount of helium gas, and you're seeing its two side views in the mirrors here, and a direct view from below. So as the pumps run up here, they're gradually pulling out all the liquid helium, they're gradually depleting this puddle, and the vacuum in which the drop is sitting is getting better and better. While that's happening, the drop definitely shrinks and loses some mass, but at some point, the vacuum seems to be very good, and the drop just doesn't seem to change for hours and hours as long as we hold on to it. So to make a more sophisticated measurement, we shine a simple laser beam through the drop and record the transmission through the drop over a period of several hours. And what we see are these funny dips every 1,000 seconds or so. And what we attribute this to is some sort of optical resonance of the light inside the drop, and the drop is slowly evaporating, and so it's tuning the cavity modes of the drop, and every once in a while coming on resonance with the laser. This gives us a very precise measurement of the evaporation rate of the cavity. We're losing sort of one wavelength of circumference every 1,000 seconds. That means a very well-known number of helium atoms per second. And because in liquid helium we know the latent heat of evaporation, and we know the heat conductivity very, very well, that means we can tell you exactly what the temperature of the drop is. And in this case, it's 342 millikelvin, which is not absurdly cold, but I should mention that we're shining 35 milliwatts of laser light on this drop. Now, if we repeat this measurement, but for different powers of the laser, we see that indeed the drop does get colder and colder as we turn down the laser power. Again, because of the well-known thermodynamic properties of helium evaporation, we can tell you how much heat is being deposited in the drop, and it's sort of picowatts. So right away, we could say that even if helium was, to our surprise, absorbing light, shining milliwatts and seeing picowatts means that it has an absorption coefficient of parts per billion. We think it should be more like parts per trillion, and in fact, we think that this extra temperature is due actually to the mirrors inside the chamber getting a bit hotter, the adsorbed helium film boiling off, and spoiling the vacuum a little bit in our chamber. So if you interpret this heat load just as a background pressure of helium, we're achieving pressures that are not UHV, but at least reasonably good for a chamber that was at an atmosphere of helium just a few hours previously, so in the 10 to the minus 8s. We can add a second laser and use the first laser to intensity modulate and try to drive via radiation pressure effects the drop's motion. And with the second laser, monitor the drop's motion. And these show the excitations in the drop's surface waves for different orders of wave, all the way up to the L equals 6 mode. So these are the mechanical resonances of the drops. of the drop. We can measure the drop's resonance frequencies as a function of its size, as it evaporates over time, for example, and as a function of the different mode, and it agrees very well with classic hydrodynamic calculation. We can measure the line width of these resonances. Again, this is shown just as a function of the surface mode index. See this trend here. It turns out that in liquid helium, unlike almost any other material, it's so well understood that you can calculate a priori the damping of surface waves due to inelastic scattering with bulk phonons. The prediction of that theory with no free parameters is shown here in the green lines. This little bit of deviation we do see over and over again, as do we see the sort of even-odd effects. We think this is due to the fact that the inelastically scattered phonons actually bounce around inside a nearly spherical cavity and interact coherently, so to speak, with the surface wave. Anyway, this is just a sort of interesting bit of liquid helium physics to explore here. So that's the last slide of this section, and really the end of my talk. What we've demonstrated so far with this experiment is that we can trap almost millimeter-sized liquid helium drops and evaporatively cool them to reasonably low temperatures. We've been able to see optical whispering gallery modes with quite modest finesse. There's a sort of technical story here about the drops being a little bit too small to really sustain those high finesse cavities, and us not having built our input coupling optics correctly to couple to the right whispering gallery modes. And this has been a project that's been in development for a long time, so I want to thank the people who worked on the prehistoric aspects of it, the people who are responsible for the results you saw today, and in particular, Charles Brown, who just graduated with his PhD and is joining Dan Stamper-Kern's group in Berkeley. So the very last thing that I want to say, I guess I have 1 minute left, so I just want to say that this idea of levitating superfluid liquid helium drops has a lot of interesting applications. We definitely want to be doing quantum optomechanics with this system, now in the milligram scale. There are also interesting questions at the foundations of fluid mechanics that this kind of perfectly isolated system should allow us to access. But the thing I want to tell you a tiny bit is about using the unique properties of liquid helium to make a precision test of physics beyond the standard model. In particular, the standard model predicts that all electrical charges should be integer multiples of the electron charge. There are extensions of the standard model that would violate this prediction to various kinds of dark matter or fifth force types of physics that would result, for example, in the electron and proton having slightly different charge magnitudes, or there being dark matter particles that might have small fractions of an electrical charge. Now, it turns out that the present state of the art in our knowledge of the equality of the electron and proton charge, which is indicated here by this blue range of parameters, was set by experiments using laser levitated micron scale glass spheres. One neutralizes the sphere and then applies large electric fields and see whether the sphere moves under the influence of those electric fields, and then says, hey, this apparently neutral object had such and such charge. Should be 0. As far as we can tell so far, it is. It turns out that the practical limitations in those measurements is due to the fact that glass microspheres can be neutralized, but they invariably have a lot of electric quadrupole, electric octupole, all kinds of electrostatic disorder that gives trouble in those experiments. Liquid helium is different in that regard in that it has no electrostatic disorder. It doesn't have broken bonds or impurities in it. Furthermore, we can levitate cubic centimeters rather than cubic microns, and we can use all of these surface modes as a sort of additional checks to rule out various kinds of backgrounds. So with those kinds of improvements, we hope that we can make measurements into this gray region and do more precise tests of things like the electrical neutrality of matter. Okay, the very, very last thing that I want to say is sort of a general advertisement. This was the title of my talk, Quantum Optomechanics. But I want to say that more broadly, in quantum optics, liquid helium has a potentially interesting role to play, not just in optomechanics. So I think usually we think of quantum optics as having two different kinds of matter that it can interact usefully with. Atomic matter, which has these parameters here, properties, it's very dilute, but homogeneous and well understood. And then solid state nonlinear materials, which are very dense. They interact really strongly with light, but they're full of disorder and hard to model, etc. Liquid helium is really unique in a middle ground between these two systems in that it combines a lot of the best aspects of both. It has the density of condensed matter material, but has no disorder. It's truly homogeneous. Its microscopic properties are understood incredibly well. You can study it as a gas, as a liquid, as a superfluid. And electronically, it's incredibly linear and boring. But because it is so compressible, it has a mechanical contribution to its optical nonlinearity that can be used for three-wave mixing type of nonlinearity, for example. So anyway, if this is of interest to you, building quantum optics devices out of liquid helium, I would love to chat more while I'm here. But for now, just thank you for your patience and for listening to this talk.
Yeah, thank you very much, Jack, for the beautiful talk. So, time for questions.
So this is really great, yeah, awesome, yeah. About this drop that you produce, what do you know about the vortices?
So you saw the video. It's a very chaotic, turbulent-looking process. Any reasonable person would assume that it ends up spinning. The drop is produced at 4 Kelvin, so it's no problem for the liquid to be undergoing rigid body rotation, and as we pump, it's getting evaporatively cooled. When we go and measure the drop, we did the most careful video analysis that we could, proper, image analysis, edge detection, fitting. I don't have slides to show you that. There was no visible centrifugal bulge. And from, video image analysis is not the way you'd want to do that. But at that level of sensitivity, we could say that there is less than 100 there's sufficiently little angular momentum that there is no more than 100 vortex lines in there. There might be some, but there's no more than 100. We have a lot of, once we have rebuilt our experiment to make bigger drops, we think we have very sensitive ways of detecting a single vortex line, measuring that vortex line, first of all, its existence, second of all, its internal excitations, its Kelvin waves, its interactions with phonons in great detail. But so far, all we can say is it doesn't seem to naturally form with a lot of vortices in it. I would also love to know whether anybody thinks that a normal sample that is prepared with some angular momentum and is evaporatively cooling, cold atom gas or liquid, does its rate of rotation or its angular momentum increase as it's evaporating or decrease or stay the same? This is a sort of physics puzzle that I don't feel I understand sufficiently well, but might tell us kind of what to expect in these experiments.
I think you thought a lot about this. The naive theorist would also say, why not tweeze the beat?
Yeah.
Is it hopeless?
It's been done, but only for drops up to about 10 or 20 microns. At that point, any bigger they become too heavy, you need kilowatts or megawatts of laser power. But it works, and the liquid helium that's in the watt of laser light stays at its just base temperature. It absorbs none of the light. So you can do laser levitation at cryogenic temperatures. But the drop won't be super big, and in particular for us, it won't be big enough to have these fun optical cavity whispering gallery modes. There might be a lot to do with laser levitated drops of liquid helium, just not with the internally stored light.
I mean, the other question is, I think it was 1 or 2 years ago, I saw some Japanese group, they were tweezing nano object in the liquid helium, so you could... is this also a way to do optomechanics in your cavity? You could put a nanosphere together with the liquid helium in there and...
Yeah, that's potentially promising. I think we have enough on our plate at this point, but anybody who's interested in trying that, I would love to talk about, because I think there are some cool things you could do.
Thanks. So as far as I understood, all the mechanical frequencies in these droplets are like far below kilohertz. So what is the plan to cool it down to quantum regime?
So there are a couple things you can do. First of all, you might, there are higher and higher order acoustic modes, shorter and shorter wavelength surface modes. There are the breathing modes, which are at high, those start at 100 kilohertz and up. But I would say we are really interested in these low order, very soft modes. And particularly what we're interested in, the fact is that when you take such a soft spring, this is a spring that is set just by the surface tension of liquid helium, which is about the softest spring you could imagine, and you have it coupled to a high finesse optical cavity, the optical spring effects become very strong. So just by putting light into these whispering gallery modes should result in a tremendous stiffening. In fact, if you go through the numbers, each photon of light in the optical whispering gallery mode should shift the mechanical frequency by about 1 hertz. So you have a bare frequency of 25 hertz, 100 hertz, something like that. Each photon in the cavity should shift it by 1 hertz. So in principle, you could stiffen the drop tremendously via optical radiation pressure and take this mode and push it up maybe into the kilohertz, tens of kilohertz, at which point, again, if the cavities are as high finesse as we hope they are, you would be in the resolved sideband regime.
I mean, if you just look at the numbers that you gave, there was one particular thing that it seems that your coupling was stronger than the oscillation frequency, and the kappa could be small enough to be sort of beyond sort of the superradiant transition. So in the naive Jens-Cummings version, you would be beyond the superradiant phase transition at 0 photons, which probably means there is some kind of instability somewhere. Did you study this somehow, or what is expected?
Not really. What I know about that regime, it's not quite Jens-Cummings because what we have is 2 harmonic oscillators coupled to each other, not a harmonic oscillator coupled to a 2-level system. So some of the physics is a little different. But in this regime, you get things like photon blockade. You get access to, you can produce non-Gaussian states through easier means than this strong projective measurement type of back action. There's a lot of theory on interesting things that happen in this regime, but so far it's been so far out of reach of the actual experiments that
So what you've shown so far, helium, in the mechanical oscillations were just density waves, right? So would it be feasible and or interesting to operate this system in a regime where you would see more of the liquid behaviors of the helium, where it's more than just density waves?
Yeah. So I think the most interesting things for that would be in samples of liquid helium that are prepared with vortex lines in them. And so you would be, okay, so in the helium-filled cavity, a sample that had a vortex line in it would have some interesting, the sound waves would have certain degeneracies lifted by the rotational properties of the liquid helium. The place where we really think that the fluid physics is most interesting is in the levitated drop. There it's directly accessible. And there, just the fact that you can rotate, that you can have uniform rotation is something that you can't really expect from any solid. The fact that that rotation in a superfluid would have to occur not via rigid body rotation, but by vortex lines, again, is something that you wouldn't have access to in a solid. So those are some of the places, the other where the quantum optomechanics would really be interestingly influenced by the fluid state. Most of the interesting fluid physics that we think about has less to do with quantum optomechanics. So in terms of fluid physics, in the study of turbulence, actual experiments on the onset and decay of turbulence are known to be strongly influenced by the details of the microscopic roughness of the chamber in which the fluid is contained. So the ability to take a levitated drop like this, which isn't touching any surface, induce turbulence in it through large amplitude surface excitations, and measure how turbulence occurs and how it eventually decays without that complication, that would be a big, interesting bit of fluid mechanics to look at. So that's one thing that we have in mind.
Okay, maybe then last question.
Coming back to that cool cavity with the acoustic and the optic wave, would it be interesting for you to cross it with a second one? Because that's what usually people do with atoms, right?
2 cavities?
Exactly.
Yeah, we've thought some about that. Not necessarily in terms of any dramatically new physics, but to solve some technical challenges. So if you have 2 crossed optical cavities, which is actually pretty natural to build with these fibers. You can just arrange them in crosses or 8-way junctions or whatever you like. if you have two crossed optical cavities, photons are naturally transferred from one cavity to the other via an acoustic wave that's sort of at 45 degrees. And that might provide a really nice way of doing this photon filtering. So if you drive light into this cavity, you have another pair of mirrors like this defining the acoustic cavity, and then you look for photons to come out of this cavity. That would provide a very nice bit of filtering such that the only light you'd expect to come out of here would be these sideband photons. You could send those to your photo detector and do the click-based strong projective measurements. So that's, but if you have other ideas, I would definitely be happy to discuss.
Okay, so I would suggest first to thank Jack again.
Thank you.